Imagine I'm thinking of a number between 1 and 100. You have to guess it. If you guess 50, and I say, too low, what do? You instinctively ignore everything below 50. You just eliminated half the possibilities in a single second. This isn't just a game, it is the fundamental logic behind one of the most efficient algorithms in computer science, binary search. Before we master binary search, we have to look at the brute force method, linear search. This is how a computer naturally reads, one item at a time. If we are looking for the number 99, the computer checks the first box. Nope. The second? Nope. It keeps going. If your data has 1,000,000 items, and your target is at the end, you have to make 1,000,000 checks. We can do better. There is a catch. The guessing game only works because 51 is always greater than 50. For binary search to work, your data must be sorted. If the numbers are random, looking at the middle tells you nothing. But if they are sorted, looking at the middle tells you everything. Constraint: data must be sorted. Here is the algorithm. We track a low point and a high point. We calculate the exact middle. If the middle number is lower than our target, we know the target, if it exists, must be to the right. So, we instantly delete the entire left half of the universe. We don't just step forward, we leap. Let's trace it. We adjust our low pointer to just past the old middle. We calculate the new middle. Compare again. Too high. We move the high pointer. We keep slicing the remaining portion in half, until we are left with exactly one item, our target. This is the divide and conquer strategy. In code, we usually implement this two ways. First, the iterative approach. We use a simple while loop. As long as our low pointer doesn't cross our high pointer, the search continues. Inside, we calculate the middle index. If the middle is lower than our target, we adjust the low pointer. This is generally preferred in production because it uses constant memory, space complexity. Second, the recursive approach. This is more elegant, but potentially dangerous. Instead of a loop, the function calls itself. Each call creates a new frame in memory. It calculates mid, checks the value, and passes the new range to a completely new instance of the function. This adds up. Instead of space, we now use log n, stack space. If the dataset is massive, this can crash your program. So, why does all this complexity matter? It comes down to big O notation. Let's visualize the performance difference as the data grows. Linear search grows directly with the data. Double the items, double the time. Binary search grows logarithmically. It barely notices the extra data. Imagine we searched for one specific person among all 8 billion people on Earth. Linear search would take 8 billion checks. That could take decades. Binary search? It would find them in just 33 checks. That is the incredible power of divide and conquer. Binary search is incredible, but there is one major catch. The array must remain sorted. What if we want to add the number 10? It belongs here, between 8 and 12. But to make room, we have to shift every single subsequent element. This shifting takes linear time. If we have billions of items, inserting is slow. What if we could search fast and insert fast? Welcome to binary search trees. We build this structure from scratch in the next video. Hit subscribe so you don't miss it.